Web apps have a lot of moving components, but at a high level, most modern web applications employ a similar general architecture, even though the particular implementations of this architecture might vary across web apps. In this video, we'll try to demystify what's going on in the general architecture of a web application. Following along with my previous two videos on networking, we'll track the HTTP request-response cycle, which is really the basis of how the web works. We'll look at how the HTTP request is processed and how the HTTP response is formed by our web app. We'll stop at each component to discuss its purpose. Now, I'll sometimes refer to specific technologies throughout this video just to help sort of frame the discussion with practical examples. Some of these technologies include Ruby, Rack, and the Sinatra framework. So even though some of the specifics I discuss might not be applicable for every web app, the general principles in this video and some of the lingo I use will be. But first, let's create a high-level picture of what's going on. The client is something that can send requests and receive responses. It's really all there is to it. For our purposes, the client will be the browser. The client is where the front-end component of our application will live. This is where the user can interact with our application to form requests and view responses. In this way, the client can send data to our application and receive data back from it. This is the whole point after all. The backend's goal is to process the request and send a response. It contains all the server-side components of our application. This will be our primary focus in this video. The term server refers to something that's listening for requests from a client and sending back responses. Sometimes this is talking about software, other times it's talking about hardware, so it can get a little bit confusing. But for now, let's just think of this as being a computer containing our server-side application code. In the middle, we have the internet. This is the whole underlying transportation system that allows the client and server to exchange messages with each other. This was the focus of the last two videos I made. Now for this video, we can collapse that whole system into a singular box. Our focus now is on what happens once the HTTP request has already arrived on the server. So let's place ourselves in the role of a web app developer. Let's determine what we need to do to process the HTTP request and form an HTTP response. From there, we will add various components to make our job easier. First of all, we need to actually capture the request coming into our server. So we could set up a server or a TCP server manually in our application code that's listening for these requests. But there's a few problems with this sort of manual approach. First of all, any incoming requests are just strings of HTTP text, and we'd have to parse this string ourselves to extract anything useful from it. Second of all, we haven't even considered what would happen if maybe multiple clients were trying to connect to our server concurrently. As of now, we only have room for one connection at a time. And really, as an app developer, we probably don't want to have to be worried with this lower level networking stuff anyways. We don't want our app's code to be involved with listening for requests. Here's where a web server comes in. Instead of setting up a basic server by ourselves, we'll use a separate application, a web server, that handles incoming HTTP requests from clients and can send back HTTP responses to clients. One major function of a web server is its handling of so-called static assets of our application. Maybe our web app uses a CSS file for styling. We don't really need to involve our application code for sending something simple and static like a CSS file back to the client. The web server will actually handle any of these requests for static assets for us and immediately send those back to the client without involving our code. If the request is not for a static asset, then more processing might need to be done. Now at this point, our web server is forwarding any requests that require some dynamic processing to our application code. We still sort of have the same problem from before, where we have to manually set up a socket or server to listen for any incoming requests from our web server. So we've kind of just extended this problem onto a new server. And we don't want to deal with this in our code. And still, we're receiving a string of HTTP from the web server, which means that we have to extract the information from that string manually. So here's where our second type of server comes in, an application server, which again, we can just think of as another application built to handle incoming requests. The application server can listen for requests from the web server for us, and it can simply call our application whenever there is a request. This way, our application code doesn't need to listen to requests. It doesn't need to interact with the lower level networking API and sockets on the computer. Better yet, when the application server calls our application, instead of sending off an unfriendly string of HTTP text, the application server can parse this HTTP text for us and send us over something more manageable for our application, like a hash or a dictionary, for example. Along the same line, when our application code needs to send back the response, instead of us having to annoyingly try to make an HTTP text response, let's let the application code return something easier, maybe an array, for an example. And then the application server can do the dirty work of actually converting this array or something else into a string of HTTP. All this means that our application code doesn't need to be concerned with HTTP anymore. Now, there has to be some standardized, agreed upon format for the request information that the application server forwards to the application code. Same thing with the response information that the application code returns to the application server. So we need some format there that's standardized. And here's where a communication protocol comes in. In the world of Ruby, this protocol is called rack. Rack says that the application should have a method named call that expects a Ruby hash with the request information. And likewise, the application should return a particular type of response, an array with the response information. Taking a step back, the web server and application server are often combined into one piece of software. What we really mean when we say that we serve our application code is that we're booting up these servers and telling them where our application code is. Once the application server knows where the application code we write is, it can call that upon any incoming requests. In the world of rack, for example, we just specify this in a configuration file. All right, let's think about what the developer still has to do to get the app working. We do get a nicely formatted request object provided to us by the application server. But even now, there's still a lot we'd have to take care of manually. To get a better feel for this, let's try to create a router for our application. A route is like an endpoint in our application. It's comprised of a request method and path. For example, maybe a get request to the /home path. Whenever we receive a get request for /home, we want to direct or route our application to execute a particular piece of code that's associated with this route. But how do we determine when the incoming request is indeed a get request for /home? Right now, we have to perform some conditional logic to do this, which doesn't sound terrible, but imagine doing it for every route, some of which might be more complex or contain parameters. And we haven't even thought about forming the response. At this point, our response value must still conform to the communication protocol we discussed from earlier. Again, it might be cumbersome to have to conform to this protocol for every route. Oh, and let's not forget about all the other common web app features that we'd still have to manually implement. Thankfully, the web has come quite a long way, and developers have tools to handle these problems for them. Frameworks were created by web developers who noticed that they had to continually solve the same types of problems over and over again and create the same types of solutions. A framework, therefore, serves as a template for our code that abstracts away those solutions that developers have already solved. All the app developer needs to do now is pretty much fill in the blanks. At first, we had to program at the HTTP level. Then it was at the level of the communication protocol, such as rack, used by our application server. Now, it's at an even higher level that's defined by whatever framework we're using, such as Sinatra. As I've already alluded to, one of the major benefits of a framework is that it gives us an easy to understand syntax for defining the routes in our application. When the application is built, the routes are stored on it. So with some help from the framework, when incoming requests come in, our app can match the request to one of these stored routes. The framework can then invoke the handler associated with that route. Frameworks also make it easy to extract parameters from our routes, which can come in the form of information the client supplies as part of the request, either as part of the URL directly or as part of the post request body. Sinatra, for example, makes both types of parameters easily accessible in a params hash. Also, frameworks are oftentimes built to be flexible. In Sinatra, instead of having to supply that 3-element array for a response that Rack expects, we can provide a variety of different response formats, and Sinatra will convert these formats to the Rack-compliant array that our application server expects. Another huge benefit of frameworks is view templates. Most of the time, our response is going to contain HTML for the browser to display. So a big job of our application is to dynamically create this HTML so that the front end of the app is customized to the user based on their request and their data. Without view templates, we'd have to build long strings of HTML ourselves using some pretty complex logic potentially to create this string. View templates allow us to separate this HTML into a distinct file, or distinct files for that matter, and they provide syntax for easily inserting values and code into that HTML. It's a way for us to use our application code to generate HTML without creating a complete mess in our main application files. Related to this is a feature called layouts, which we could think of as wrappers for our view templates. And layouts contain the HTML that all of our code templates, or maybe many of our code templates, will need to share. And then we can use these layouts whenever rendering a template. Frameworks also give us a unified place to store static assets for our application. Instead of us having to tell the web server where static assets are located, the framework tells us where to store the static assets, for example, in a public subdirectory, and then our framework will make that known to the server. So now, when the web server receives a request for a static asset, for example, the CSS of our application, the web server already knows where to look. What if we want to store data that persists across multiple requests? Say we want to allow a user to stay logged in across multiple requests. We need some way to indicate that the user on the browser is still logged in. One way to do this would be to store the user's ID in a cookie on the browser. But to do this manually would be tedious. We'd have to inject the cookie data into the response and parse cookie data coming in from the requests. So yet again, frameworks take care of this tedious stuff for us. In Sinatra, storing data in cookie-based sessions is easy. We just read and write data to a built-in hash called session. But what if we want to store application-related data for a long time such that it's universally accessible anywhere by the application? We could try to somehow store this in a file with our application code maybe, but over time, reading and writing to and from this file would become inefficient and annoying. We have yet another component meant specifically for storing and managing data in the most efficient way possible, and that component is the database. Usually, the database is a fully separate component in our application, a whole separate server dedicated to storing and managing the data. We connect to this database with a database client, which might be provided by the framework itself or a separate library. Our application code can use this database client to send a request to the database server as necessary. In the case of a relational database, this request will contain SQL or SQL, depending on how you pronounce it, that will be used to interact with the database. And the database server will process that SQL and either select, insert, update, or delete data from the database, striving to do it as efficiently as possible. One thing we haven't mentioned at all yet is security. Modern web apps often use user input from their requests to maybe query the database or help us generate the HTML. For example, if a user provides a search filter, we might use that in an SQL query. A malicious user could formulate input in such a way that it could cause problems to our database or maybe reveal sensitive data. Here comes yet another benefit of frameworks and related libraries. They provide ways to safely insert user input into our SQL or HTML, usually by escaping any special characters. But even still, we've just dipped our toes in the water of services available to web developers. Developers have countless external libraries they can pick and choose from to provide all sorts of functionality for their app. Even the built-in standard library of the programming language used to build our app likely has much to offer. Finally, we probably don't want to have to run our web server, application server, and database server all on our local machine. It would be much better if there were more powerful computers to do this for us. So let's deploy our application, outsourcing our application code and all its configurations to a remote server. Now, the web, application, and database servers that were really just software assisting our application on our own local machine are now running on external hardware whose primary job is to host applications and databases for production purposes. Clients no longer make requests to our computer, but rather to a remote server. For example, Heroku might be an example of a commonly used service for deploying applications remotely. Together, all of these components allow us, the app developer, to focus pretty much solely on the business logic of our app. We never have to reinvent the wheel. We're no longer limited to websites that just request static HTML files from. Without much hassle, we can create fully fledged web apps that can generate dynamic content and interact with large amounts of data. And we can use scalable cloud servers to handle our application processes and its database. In real-world applications, there are probably many more components than what this diagram has to offer. For instance, in recent years, much of the dynamic work of the web application has moved to the client to reduce the load on servers and make web apps faster. Instead of rendering HTML on the server, for example, client-side frameworks might perform rendering entirely with JavaScript running on the browser. But nevertheless, the core structure of this diagram still holds. Hopefully you now have a bit more perspective on all the tools you're utilizing when you develop a web application, often without even knowing it. Thanks for watching.